What we have seen so far is that particles in quantum mechanics can exhibit wave behavior. And this wave behavior manifests itself, for instance, with interferences when we have a particle able to go through, for instance, two slits at the same time. But this is a quantum effect because in order to observe these interferences, we need to have action of the order of h bar or even smaller. So what about light? Light is particular because we knew about its wave nature well before quantum mechanics was developed. And in particular, we knew that light was made of electromagnetic wave. And these waves are described by the well-known Maxwell wave equation. So you will see more about electromagnetic wave and Maxwell equation later. But what's important to note here is that the Maxwell equations do not have h bar in them. So how come wave behavior come from quantum mechanics if there is no h bar in it? Does it mean that light is a particular case or not? Does it mean that light has only electromagnetic waves and no particle equivalent? That's the type of questions we are going to answer in the next few minutes. Exceptionally, we will take an historical approach. So in 1900, people were interested in a problem of the blackbody radiation. So what is a blackbody? It's essentially a cavity which is heated at some temperature T, and because of its heat, it emits a lot of electromagnetic waves, a lot of light. So all the waves, the light which is emitted from the cavity is absorbed at another point of the cavity. It's called a black body, but it's misleading because if you open a small hole in this cavity and you look inside, you will see it's not black, it's more likely to be red because of the heat. It's like an oven, if you want. So, fine. People were interested to understand the behavior of the intensity of light as a function of the wavelength. So as the function of the color for visible light, if you want. So they were doing measurements, and theorists were trying to interpret these measurements. And one of these theorists is Planck. And Planck came up with a formula which reproduces the experimental measurement, where nu is the frequency of the light and it's expressed as c divided by the wavelength lambda, and c is the speed of light. It's the first time the Planck constant h was introduced in physics. Now we more often use h bar, which is a reduced Planck constant and which is just h divided by 2 pi. In order to obtain his formula, Planck had to assume that the exchange of energy between the light and the cavity had to process by quanta of energy h nu. Einstein went further than that, and in 1905 he introduced the concept of light quanta. So the light itself is made of small quantum of energy, and we now call this light quanta as a photon, which is nothing but a particle of light. And in order to reproduce the Planck formula, Einstein had to define the energy of the photon as E equal h nu. So we used this historical interlude in order to define what was the energy of the photon. And now that we have this particle of light and we know what is its energy, we can apply what we have learned so far about quantum mechanics, and in particular using the many-path formulation of quantum mechanics, in order to express the amplitude of probability for the photon, the particle of light, to go from one event to another. the energy we define for the photon, E equal h nu, is for a photon, which is a free particle, so without interaction in a potential. So it's like a kinetic energy, if you want. So in order to calculate the action, we just have the kinetic energy term, and in the case of a photon, it is just h nu. And it's a constant, therefore the action is simply written as the time integral of a constant, so that's just this constant, h nu, times the time t between the two events. So we see that when we substitute S into the expression of the amplitude of probability phi, the phase doesn't have h bar anymore, it disappears. So although we are using a full quantum treatment, the many-path formulation of quantum mechanics for the photon, it's interesting to see that there is no h bar anymore, and that therefore if we derive a wave equation for light, we will get the Maxwell equation, and there will be no h bar in the expression, which makes light appears to us as a classical electromagnetic wave.